Chemistry. We're going to do this one in multiple parts. I think I've got about 7, can't remember. But the first part of it will be done with 19 on the first part of the exam. Again, I'm splitting the exam up. So the first part of electrochemistry is definitions. And some of these will be real familiar. Okay? Electrochemistry is the relationship between electron transfer and chemical reactions. So in some chemical reactions, we're going to transfer electrons, and other ones we're not. Okay, electricity is the transfer of electrons. So when electrons are transferred, it's electricity. When you use it by plugging into the wall, then that current has been generated a variety of ways, mostly by heat. How the heat is formed is variable. Okay, but the study of chemical reactions that produce electrical currents or voltage, and voltage we'll get through that definition later, but these are the movements of electrons. So we're going to study reactions that either produce electrical currents or voltage or are caused by the action of currents or voltage. There's going to be a problem like this in the lab. It's called electrolysis, and we'll go through that in detail here, but also in the lab. Okay, so basically electrochemistry is how you get electrons that you can use elsewhere in a chemical reaction. Okay, the first step is definitions that should be familiar to you, because oxidation is loss of electrons. We can say it's oxidized, or it's the reducing agent, or the reducer. So the oxidized means the species is oxidized. But if it's oxidized, then it causes reduction, so it's the reducing agent or the reducer. Reduction, on the other hand, is gain of electrons. And so a substance is reduced. And if it's reduced, it causes oxidation, so it's the oxidizing agent or the oxidizer. Okay? Now, this is really the hard part, is keep remembering what oxidation and reduction is, because you also have to remember that oxidation and reduction must occur simultaneously. That means you can't have one without the other. You can't have just oxidation, it has to be reduced. Now, oxidation differs from oxidation states because oxidation states are not concrete. What they are is the number of electrons lost or gained by an atom. Okay, so valence numbers are real. Hydrogen has 1 electron, chlorine has 7. But oxidation states are variable because hydrogen can lose 1 proton, 1 electron and be H plus. It can gain 1 and be H minus. And chlorine can gain 1 or lose up to 7. So remember, valence electrons or valence numbers are actual real numbers. Oxidation states are variable based upon whether you're losing or gaining. Now, as I said, the most important part is knowing what's oxidized and what's reduced. So you can use either of these mnemonics: loss of electrons is oxidation. I don't do that well. Gain of electrons is reduction. It's one way to remember it. Other way is oxidation is loss. Reduction is gain. Okay, now, honest to goodness, in this chapter, you're going to constantly be asking yourself, wait, did it lose electrons or did it gain electrons? And is gaining them, what's gaining them? That's reduction. So, now, the other ugly part is, remember, electrons are negative. So if you add electrons, you become more negative. If you lose electrons, then you're more positive. Because a lot of times people think, oh, you're more positive, therefore you gain them. No, no, no. It's opposite because the charge of electrons are opposite. Okay. So determining oxidation and reduction. Well, the first thing we've got to do is determine the oxidation states. So if we look at this, this is a simple problem. Now, we're not going to balance it. Balancing redox reactions is actually a little harder than balancing regulars. More about that. But I'm going to balance this one later. But right now, I want to determine whether it's an oxidation or reduction. The easiest thing to do is look at it. And these are all charges. So this one's 4 plus. This one's 2 plus. This one's 3 plus, and this one's 4 plus. So if we look at cerium, we're going from 4 plus to 3 plus. And for tin, we're going to go from 2 plus to 4 plus. So if we look at it here, we gained electrons. Gained electrons. And here we lost electrons. So that means this one's reduced, or red, and this one's oxidized, or ox. Remember, red equals reduced, and ox equals oxidized, because nobody wants to keep writing that. That's why we refer to these as redox reactions. Okay, so this one's really straightforward. This one's going to be a little more complicated. So here we go. Manganese 4 oxide, it reacts with hydrogen gas. So here's our reaction. The question is this a redox reaction? Give the oxidation numbers of all atoms that change oxidation number. So if you'll remember back in chapter 4 in this text, I believe, when we did oxidation numbers, we're going to do oxidation numbers. Remember, if it's a neutral compound, the oxidation numbers have to balance, add to 0. And remember, oxidation numbers are per atom. Okay, so we're going to start with oxygen because it's easier. It's 2 minus. There are 2 of them. So that's 4 minus. So that means manganese here has to be 4 plus, which if you notice the name, you're like, oh, wait, it's 4. Okay, we're good. Hydrogen, remember, elemental states are 0, so this one's 0. I will try to, I'm pretty sure I've already posted the oxidation rules from 1211, but I will make sure they're posted so you can look at those. So back over here, we have oxygen is still 2 minus, so there are 3 of them. 2 minus times 3 is 6 minus, so manganese here has to be 3 plus. Oxygen here is 2 minus. There are 2 hydrogens, so it's 1 plus. So the question is this a redox reaction? Well, did anything change? Well, manganese went from 4 plus to 3 plus, What else changed? Hydrogen changed. It went from 0 to 1 plus. So this one lost electrons, so it's oxidized. This one gained electrons, so it's reduced. So we said, okay, what gets reduced? Manganese, which gets oxidized, hydrogen. So that means that since manganese was reduced, it's the oxidizing agent, and since hydrogen was oxidized, it's the reducing agent. Now, the beauty, ugliness of electrochemistry is they like to use the same word in different definitions depending upon the context. So, oxidized is different than oxidizing agent. So, be aware of that when you're asked questions. Okay? So, we need to bone up on our oxidation numbers, and remember, don't put them on top, because if you put them on top, then that implies an ion, and that's not what you want. So we're going to look at here. Iron is an elemental, so it's 0. Chlorine is a diatomic, which is its elemental state, so it's 0. So chloride here is 1 minus. Iron has to be 3 plus because there are 3 chlorides, and 3 minus has to equal 3 plus. And so this is asking for the oxidizing and reducing agents. So let's go ahead and identify what's oxidized and reduced. The agents are the opposite. And so iron is going from 0 to 3 plus. Chlorine is going from 0 to 1 minus. So this lost electron, so this is oxidized and this is reduced. Okay? Here we have hydrogen is 0 because that's its elemental form. Same with oxygen. Hydrogen here is 1 plus. Oxygen is 2 minus. Notice we're putting the oxidation numbers for each atom. We don't care how many atoms you have. There are 2 hydrogen atoms, so the total charge on the hydrogen is 2 plus. We need that for finding the oxidation number, but we're only concerned with per atom. So hydrogen here is going from 0 to 1 plus, and oxygen is going from 0 to 2 minus. So gaining electrons is red and it's ox. And I'll give you a hint. Sometimes one of them is easier to see than the other one. So once you've got one, you've got the other one. This one here is going to be interesting because we have different compounds mixed up. Copper has no charge, so it's 0. Oxygen, we want to do oxygen first because nitrogen is variable, so that's 2 minus. There are 3 of them. So that means that you have a total charge of 6 minus here. And because there is a charge on this species, we have to equal 1 minus. Therefore, nitrogen have to add to 6 plus to give us 1 minus. So it's 5 plus. Okay? Oxygen is 2 minus. Hydrogen is 1 plus because we've got a positive charge here. Charge on copper here is 2 plus. Oxygen is still 2 minus. There are 2 of them, so that's 4 minus. So nitrogen has to be 4 plus. Hydrogen is 1 plus, and oxygen is 2 minus. Now, once we got all the oxidation numbers, we look at it and go, whoa, who changed? So copper went from 0 to 2 plus. And then you're like, nothing, wait. Nitrogen changed. Nitrogen went from 5 plus to 4 plus. So copper here was oxidized because it lost electrons, and nitrogen was reduced because it gained an electron. Okay. Carbon here is 0, oxygen here is 0, oxygen is 2 minus, that means carbon is 4 plus, so carbon went from 0 to 4 plus, and oxygen went from 0 to 2 minus, so this is reduced and this is oxidized. Okay? Now, the last one here is this long equation. So we have Iron is 2 plus. Oxygen is 2 minus. There are 7 of them. So that's 14 minus. Has to equal the charge, which is 2 minus. So the chromium here has to be 12 plus. But there are 2 of them, so each chromium is 6 plus. Oxygen is 2 minus. Hydrogen is 1 plus. Okay, I just made that into a hydrogen for fun and entertainment. 1 plus. Iron here is 3 plus. Chromium is 3 plus. Hydrogen is 1 plus. Oxygen is 2 minus. Therefore, when we look at it, we've got iron going from 2 plus to 3 plus. We've got chromium moving from 6 plus to 3 plus. So this one's reduced and this one is oxidized because iron lost electrons, it is oxidized, and chromium gained electrons, so it is reduced. Now, this is critical that you understand oxidation numbers and can do them at will. Again, there are extra ones posted with the rules. Go back and refresh your memory. Remember, just go figure out and make sure you know how to do it, okay? All right. So, here's the other thing about oxidation numbers is redox occurs everywhere. These reactions that I showed you are what we refer to as inorganic reactions. And they're straightforward. This class is inorganic, but they do occur in organic compounds, but they're different because in organic compounds you usually don't see the electrons moving unless you see the transfers. It's called the mechanism. But basically what you see them is the number of bonds and the type of bonds. Okay, so we're looking at the type and number of bonds. And it's between carbon, which is the main atom in organic compounds, and hydrogen versus carbon and oxygen in any other electronegative species. So, oxidation is still the loss of electrons. Okay, but the way you see it is that something is oxidized in an organic compound if you decrease the number of carbon-hydrogen bonds while the number of oxygen bonds, and it can be oxygen, nitrogen, or any of the halides or sulfur, go up. So basically, look at your carbon-hydrogen bonds. Okay, reduction, on the other hand, is still the gain of electrons. But in this case, the carbon-oxygen, halide, nitrogen, whatever, go up, but the carbon-hydrogen bonds go down. So, excuse me, I'll just reverse that. Let me erase that. The number of carbon-oxygen bonds go down. They can't both go down while the carbon-hydrogen bonds go up. So the bottom line is if you have more carbon-hydrogen bonds, that's the reduction. If you have less carbon-hydrogen bonds, that's what's oxidized. Okay, and the other way to think about it is oxidation, or the oxidized species, has more oxygen in it. Okay, which is a simple way to think about it. Now, how does this present? Well, we have ethanol here and we have acetic acid. So if we're counting bonds, we're going to count this as one carbon-oxygen bond. Okay? Over here, we're going to count it as one here, and one here. So on this one, you have one carbon-oxygen bond. Over here, you have 3 carbon-oxygen bonds. So in this case, it has increased carbon-oxygen bonds. So this is the oxidized form. So this has to be the reduced form. Okay, because they're paired. So the reduced form gets oxidized. Okay, now this becomes important because in biology you're going to talk about the citric acid cycle. You're going to talk about the movement of all kinds of things like nicotine, adeno, I forgot what NAD is, NAD and NADH. Now the difference is, notice that here we have the H and here we don't have the H. So what is going on here is we're transferring electrons via bonds, which is really a transfer of energy. Okay, so if we look at it, we have the isocitrate and we have the alpha ketoglutarate, and you're like, do I have to pronounce that? No, you don't have to pronounce that. But let's look at the bottom unit here. Okay, you have one carbon-oxygen bond. Here you have two here, and you have this one you really kind of can't see, but it's the same thing we saw before. So it's 3 bonds here. So if you look at the final one, these are basically, well, this is the same as this. Let me box it. So the only difference is this has 2 oxygen-carbon bonds. This one only has 1 carbon-oxygen bond. It's different. So if that's the case, this one's reduced and this one's oxidized. And so if we're looking up here, they pair. So this is the reduced form and this is the oxidized form, because remember, this one has the extra hydrogen. So on a test situation, you likely have one, but you're likely to have it look more like this than this. If it does look like this, I'm going to tell you which area to look at. Because if you'll notice, this carbon, let me change colors. These carbons are the same. These get weird, but they're pretty much the same. But this is part of the citric acid cycle. So the point being is be able to do like this one. More than anything else. And again, this becomes critical in organic because we look at the number of bonds. So this is the end of the first definitions.